How are you guys
Good
doing?
evening, Professor.
All right, okay. Okay, let's do more.
Professor, can I ask one more question?
Yeah, sure.
If it would be possible for you just to set up problem 224.
224, hang on a second.
Thank you.
Okay, just okay. So homework question. Problem number 224. A cart that is free to move. And to this cart, we have a double pendulum attached. This is 2M. This is M. And this is also M. This is B, and this is B. Let's run. This will be the. Now let's write it as X. And this will be as Y. And we have this one as theta 1. This is theta 2. Now let's say this is the X of the cart, all right? So we have a system with 3 degrees of freedom. Our goal will be to find L, which is T minus V, and then write the equations, all right? And we have Q1 equals to X of the cart, Q2 equals to theta 1, and Q3 will be theta 2. Yeah. What's the question? I can't hear you. Somebody say something. I can't hear you. Well, either say something or turn off your mic, all right? So T is kinetic energy, right? So let's start with potential energy. V. Somebody turn off your mic. V equals to potential energy. Let's call this, right, it's going to be minus mg of B cos of theta 1. That's for this mass. Minus mg, and that's going to be vertical coordinate will be B cos of theta 1 plus cos of theta 2. So far, so good?
Yes.
All right, good. All right. The cart has no potential energy, right? The T. It's going to be T cart plus T, let's call M1 plus TM2, right? T cart is easy. It's going to be 1/2 of 2m times x dot squared. Okay. The TM1 equals to 1/2 of m times V1 squared, right? Now, V1 squared we need to find, all right? V1 vector equals to V1 relative to M1 plus the V of M1 plus, sorry, not relative to M1, just a second. Relative to cart plus V1 of the cart. Now, V of the cart is known, so V1 of the cart is known, and that's x dot I, right? A V of the pendulum, one relative to the cart, will be, let's just make a picture, local picture, and we'll see that's the θ1. So the relative to the cart, it will be this one. So it will form an angle θ1 with horizontal. That's V1 relative to the cart. And numerically, it will be equal to ω1. So there's going to be θ1 dot times b. That's the value of this one. And times the direction unit vector, which is going to be cos, hang on a second, b times cosine of θ1, that's horizontal one, right? Times I minus sine of θ1 times j, because our y is directed downwards, right? Okay. So the result is that V1 total equals to x dot plus θ1 dot b cos of θ1 times I and plus θ1, pardon me, θ1 dot b sine of θ1 with a minus times j. Now we need only the square of this, so we'll do the square. So V1 squared equals to x dot plus θ1 dot b cos θ1 squared plus minus θ1 dot b sine θ1 squared. This will be x dot squared plus 2x dot θ1 dot b cos θ, and plus this square will be just θ1 dot b squared, θ1 dot b squared. That's the V1 squared. And then we'll have the TM1. That's the second part of kinetic energy, TM1 equals to 1/2 of m times x dot squared plus 2x dot θ1 dot b cos θ plus θ1 squared b squared. So far, so good?
Yes.
All right. Now, the T of M2, of course, is going to be 1/2 of m V2 squared. Now we're going to write down what the V2 squared is, and we'll write down now from scratch so you will see it, right? Okay. V2, of course, equals to R2 dot. Let's find out what the R2 is. R2 equals to. It's going to be Xi, that's there, right? Okay. Plus, on the horizontal component is going to be the, pardon me, B sine of theta 1 plus B sine of theta 2 times I, and plus the vertical one will be minus B, no, plus B cos theta 1 plus B cos theta 2 times J. Is this clear?
Yes.
Okay. Now we time differentiate it to get to the velocity. V2 equals to dr2 over dt, and that's going to be x dot I plus B, in parentheses, will be cosine of theta 1 times theta 1 dot plus cosine of theta 2 dot times I minus B sine of theta 1 times theta 1 dot plus sine of theta 2 times theta 2 dot. So far, how is it coming?
Makes sense. Thank you.
All right, okay. So we need the V2 squared, and that's going to be x dot plus B cos theta 1 times theta 1 dot plus cos theta 2 dot. All of that squared, that's the I component. By the way, here I forgot to write J, right? Okay. Squared and plus B squared, and there's going to be sine of theta 1 times theta 1 dot plus sine of theta 2 dot squared. Now we have to square and carefully combine the pieces. So here we have three terms, so we'll have x dot squared plus b squared, and there will be square of this parenthesis, which is going to be cosine square of theta 1 times theta 1 dot squared plus cosine square of theta 2 times theta 2 dot squared plus 2 cosine theta 1 cosine theta 2 theta 1 dot theta 2 dot, and plus the double product here, which is going to be 2 plus 2 x dot b, and there's going to be cosine of theta 1 times theta 1 dot plus cosine of theta 2 times theta 2 dot. That's the square of the I piece. Now the square of the j piece is going to be plus b squared, and inside you will have sine squared of theta 1 times theta 1 dot squared plus sine square of theta 2 times theta 2 dot squared plus 2 sine of theta 1 sine of theta 2 times theta 1 dot, theta 2 dot. Now we'll combine whatever we can to simplify things. X dot squared, that stays there, plus, let's see, b squared cosine squared this, b squared sine squared this, that's going to plus b squared theta 1 dot squared, that's 1. But then we'll have this one and this one, plus b squared theta 2 dot squared, okay? Then we'll combine this one with this one, all right? You'll have this one and this one, plus b squared times 2 times cosine of theta 1, cosine of theta 2, plus sine of theta 1, sine of theta 2, both multiplied by theta 1 dot, theta 2 dot. Almost there. And we have this extra piece dangling around. It's going to be plus 2 bx dot cosine of theta 1 times theta 1 dot plus cosine of theta 2, theta 2 dot. Now this piece here is, pardon me, is cosine of a difference, cosine of theta 1 minus theta 2. It's going to help a little bit. So the result will be x dot squared plus b squared, and we can break it like this, theta 1 dot squared plus theta 2 dot squared plus 2b squared theta 1 dot theta 2 dot cosine of theta 1 minus theta 2, and plus 2bx dot cosine of theta 1 times theta 1 dot plus cosine of theta 2, theta 2 dot. We now have all the building blocks for the kinetic energy. It's big, but well, what can you do there, right? Okay. So kinetic energy will be equal to the sum of these three pieces. Let's see where the first one is. Okay. 1/2 of x dot or so. And that's going to be this one, right? Okay. It's going to be mx dot squared. That's for the cart. Mx dot squared plus the first mass is this one. I'll just copy it there. Okay. And plus the last one, which is going to be 1/2 of m. That will be x dot squared plus b squared theta 1 dot squared plus theta 2 dot squared plus 2b theta 1 dot theta 2 dot cos of theta 1 minus theta 2 and plus 2b x dot cos of theta 1 times theta 1 dot plus cos of theta 2 times theta 2 dot. And now let's try to combine these pieces. We'll have this one and this one and this one. And that's going to be 2m x dot squared. All right. Now, we'll have, this is, okay, I missed this. So we then have 1/2 m this, and we have this 1/2 m. That's going to be m theta 1 dot b squared plus m theta 1 dot squared b squared, right? Plus 1/2 m b squared theta 2 dot squared. And plus the other two pieces. Well, let's see. This one has no pair. It's going to be plus 2b theta 1 dot theta 2 dot cos of theta 1 minus theta 2 plus bx dot cosine, and we have the bx dot cosine. It's going to be one piece here with 1/2 mass, and this one piece here, all right? So plus 2 times 1/2 will cancel out. This is going to be 2mb x dot theta 1 dot cosine of theta 1. And what's left is this one plus 2b, oh, pardon me. Plus okay. Plus this term will be 1/2 times 2 will be 1. So it's going to be m b x dot cosine of theta 2 times theta 2 dot. That's going to be the expression for the kinetic energy. All right. And then we'll write down the equations of motion. The first one is, do I need to write down the equation of motion, or you already know what to do after that?
No, I was just curious if my process was right. So yeah, we can
Okay.
stop here.
All right.
Unless somebody else needs it.
So then you will need to do the d, sorry, d over dt of dl. Actually, we can put not L, we can put the T directly. dt over dx dot minus dl over dx. But dl over dx equals to, let's see, dl over dx. Yeah, dl over dx is 0, right? Okay. Is it 0? Yeah, okay. Equals to 0. So here the dt over dx dot is constant, right? Okay. That's one of the things. Then you have d over dt of dt over d theta 1 dot, not dl, no, dt, minus dl over d theta 1 equals to 0. I use the fact that the v is not a function of theta 1 dot, right? Okay. And then the next one will be d over dt of dt over d theta 2 dot minus dl over d theta 2 equals to 0. So you have to do the derivatives. Okay. Does it clear up your picture?
Yes, thank you.
All right, good. I want to review again quickly the derivation of the Euler-Lagrange equations, because we'll need to go to some cases which will be important, all right? So back to elements of variational calculus. Recall we want to have S, which is integral of we use the x1 to x2 of L of x, y, and y prime dx to go to minimum with boundary conditions of y of x1 equals to y1 and y of x2 equals to y2. And we did it by taking the variation delta s. That was integral from x1 to x2 of dl over dy1 delta y1 plus dl over dy2 delta y2 dx to be 0. Sorry, not y1. I'm sorry. It's not y1, y2. It's not the y1. A little bit ahead of myself. Okay. This is dy prime equals to 0. And we'll write down that the integral of from x1 to x2, the second integral of dl over dy1 delta y1 prime. No y1, just y. Why did I put this? Y prime, dy prime, dx will be equal to, we'll go by parts. That okay. I don't think I'm right. Just a second. And this will be d over dx of dy delta y. All right. So by parts, this will be dv, and this will be u. So it's going to be dl over dy prime times delta y from x1 to x2 minus integral of d over dt of dl dx, sorry. d over dx of dl over dy prime times delta y dx. And this integral is, and this increment is 0 because delta y of x1 equals to delta y of x2, and it's 0. So y is delta y is variation, but it has to be constant at the ends. So the result, it will be minus integral from x1 to x2 of d over dx of dl over dy prime times delta y dx. And so the result is that variation of s, which has to be equal to 0, is actually equal to integral from x1 to x2 of dl over dy minus d over dx of dl over dy prime, all of that times delta y, which is arbitrary variation, arbitrary inside but not at the ends. And since it's arbitrary, we require that the bracket inside will be 0. So here we have that the dl over dy minus d over dx of dl over dy prime equals to 0. And that's the Euler-Lagrange equation. Okay. We now go to the examples that your book has. There's quite a lot of them. Are you guys done with this page?
Yes.
Example 1. Write out Euler-Lagrange equations for finding the extremals. All right. Right. Euler-Lagrange equation. Well, that's number 3, 4. Let's take number 2b. All right. So here the L, or I called it L, they have F. So F of x, y prime equals to y prime squared minus y squared. So we have the df over dy equals to minus 2y. F over dy prime equals to 2y prime. D over dx of df over dy prime equals to 2y double prime. And so the equations will be minus 2y minus 2y double prime equals to 0. Simplifying, we get y double prime plus y is 0. Make sense? Let's do one more example. Number 3.5b. So the f of x, y, and y prime is equal to y squared plus y prime squared plus 2y e to the x. So here df over dy equals to 2y plus 2e to the x. Df over dy prime equals to 2y prime. D over dx over df over dy prime equals to 2y double prime. The result of this will have that 2y plus 2e to the x minus 2y double prime equals to 0. So that means y double prime minus y equals to e to the x. Any questions so far? To the next page. Number 3.6. Find extremals with given boundary conditions. So we have S equals to interval from 0 to pi of, that's going to be A, right, of y of x squared plus y prime of x squared minus 2y of x sine x dx. All right. So we want S to go to minimum. And that means you will have that df over dy minus d over dx of df over dy prime equals to 0. Df over dy equals to d over dy of y squared plus y prime squared plus minus 2y sine x. It's 2y sine x. And that's going to be 2y minus 2 sine x. df over dy prime equals to 2y prime. So d over dx of df over dy prime equals to 2y double prime. So we'll have that 2y minus 2 sine x minus 2y double prime equals to 0. Bringing it to one side and dividing by 2, we'll have y double prime minus y equals to minus 2 sine x. And the boundary, and the boundary conditions are y of 0 equals to y of pi equals to 0. Right? So we'll solve this equation, this non-homogeneous equation. So we'll have y equals to yh plus yp. The yh double prime minus yh equals to 0. Try yh equals to e to the rx. R squared minus 1 is 0. R equals to plus minus 1. And we have that the yh equals to, you can either use the exponents or you can combine them into hyperbolic functions. I'll use the exponents. It's going to be a e to the x plus b e to the minus x, all right? Now y particular, try y particular in the form of c sine x. Then y particular double prime equals to minus c sine x, right? So we have minus c sine x and minus c sine x equals to minus 2 sine x. Minus 2c sine x equals to minus 2 sine x. So clear that c equals to 1. And we have the y particular equals to sine x. So y equals to a e to the x plus b e to the minus x plus sine x. That's the general solution. Now we use the boundary conditions. Y of 0 is supposed to be equal to 0. And that will be a times 1 plus b times 1 plus 0. Therefore, a plus b is 0, and b equals to minus a. So y general becomes, at this point, a times e to the x minus e to the minus x plus sine x. Now y of pi is 0. That means a times e to the pi minus e to the minus pi plus sine of pi, which is 0, equals to 0. That means that a is 0. Okay, so y equals to just sine x. That's the solution to this problem. Okay, now generalization. Suppose S equals to integral from, let's make it from T1 to T2 of T y of t, y dot of t, dt. and we need to run it to minimum. Here, y tilde equals to y1 of t, y2 of t, and etc. yn of t. And they're all independent. We'll go through similar steps, going through similar steps, but with the column vector through similar steps. We'll have that the integral from t1 to t2. Oh, sorry, there is an L here, or F right there, right? Of df over dy tilde, dy tilde minus d over dt of df over dy prime tilde times delta y, right there, right? Times dt equals to 0. Here, what this means is actually dot product, all right? So here is what happens here. df over dy tilde is df over dy1 all the way to df over dyn. Df over dy dot will be is df over dy1 dot, df over dy2 dot, all the way to df over dyn dot. If you call this thing here as a column vector tau, then integral of tau dot delta y dt from t1 to t2 is 0. It means that the following thing is from t1 to t2 is tau 1 times delta y1 plus tau 2 times delta y2 plus etc. plus tau n delta yn dt equals to 0. Now, in this case, since y1 all the way to yn are independent, therefore delta y1, etc., delta yn are also independent functions. Therefore, this star condition, since they're independent, that means star is in fact means integral of tau 1 delta y1 dt from t1 to t2 is 0. Integral from t1 to t2 of tau 2 delta y2 dt is 0, and etc. until the nth term. So in other words, we vary these variations independently for each subscript. And since these are supposed to be, and since these are arbitrary, it leads to tau 1 equals to 0, tau 2 equals to 0, etc. Tau n equals to 0, which means df over dy1 minus d of dt of df over dy1 dot equals to 0, and all the way to the nth one, df over dyn minus d of dt df over dyn dot equals to 0. So we derived that if we have not one unknown function y, but a whole column vector of these functions, then for each of the components, we have the same Lagrange Euler equations, and we can solve it. All right. Example. Yeah, let's see where the examples are. We don't have that many examples here. Well, let's try this one. Number 310. Here, the I of U and V, that's what I call S, equals to interval from 0 to 1 of U prime squared plus V prime squared plus pi squared over 2 UV dx, with boundary conditions are U of 0 equals to 0, U of 1 equals to 1, V of 0 equals to 0, a V of 1 equals to negative 1. Find the U and V as functions of x. This is a clear case of what we discussed before, y being U and V, right? So we'll do this thing clearly. And we have df over du equals to pi squared over 2 times v. Df over du prime equals to 2 u prime. D over dx of df over du prime equals to 2 u double prime. Okay, so the first equation will be pi squared over 2v minus 2 u double prime equals to 0. That's equation 1. All right. Now that we'll go through the same thing with this one. Since it's symmetric, we'll get similarly, we get pi squared over 2 times u minus 2v double prime equals to 0. Now we need to solve this system of equations. In order to solve it, let's take one of the equations, for example, equation 2, And to get u double prime there, we have a d squared over dx squared of equation 2. The result will be pi squared over 2 u double prime minus 2v fourth derivative equals to 0. Now, from equation 1, you have that u double prime equals to pi squared over 4v. Plug in here, and we have pi squared over 2 times pi squared over 4v minus 2v fourth power equals to 0. We'll divide by 2, and we have fourth power of v minus pi squared over 16v equals to 0. Did I do the boundary conditions? Yeah, we have u of 0, u of 1, v of 0, v of 1, right? Okay. So we'll have to figure something out, because for this one we need 4 boundary conditions, but we just have 2 for v, right? Okay, so we have that v equals to e to the power of r x, then r to the fourth minus pi squared over 16 equals to 0. R 1 and 2 equals 2 plus minus pi over 4. And R 3 and 4 equals 2 plus minus pi over 4 times I. We use the fact that I to the fourth is 1. Therefore, we have the following. We have that v equals to, let's, instead of e to the power of this, we'll use the hyperbolic function. It's going to be a cosh of pi over 4x plus b sinh of pi over 4x plus c cos of pi over 4x plus d sine of pi over 4x. All right, that's the v. Let's try to find the u, because we found this thing here. A u double prime, okay. U double prime equals to pi squared over 4v. Let's look at this. U double prime equals to pi squared over 4 times v. All right, which is pi squared over 4. And we have these things, a cosh of pi over 4x plus b sinh of pi over 4x plus c cos of pi over 4x plus d sine of pi over 4x. This is all nice, but let's try to simplify it, because if we have some of the boundary conditions, may be helping us out, right? We have u of 0 equals to 0, u of 1 equals to 1. Okay. U of 0 equals to 0. And that's going to be a times 1 plus b times 0 plus c times 1 plus d times 0. And that's 0. That means a plus c is 0. So c equals to minus a. Okay. Therefore, v equals to a cosh of pi over 4x plus b sinh of pi over 4x minus a cos of pi over 4x and plus d, pardon me, sine of pi over 4x. That's the v. And let's see, with U, if we integrate, we'll have two more constants, all right? So that's going to be way too many constants. Is there any way to avoid this thing? Let's see, we'll look at this system. So this way of solving it is kind of, it's okay, it's not incorrect, but it's kind of inefficient. Kind of inefficient because we don't get enough equations to find these things. So instead, let's try matrix approach. Let's try the following. We'll have u double prime equals to pi over phi squared with 2v. U double prime equals to pi squared over 4v. And v double prime equals to pi squared over 4u, right? Okay. Let's write it down in matrix form. It's going to be uv double prime equals to pi squared over 4 uv, and this will be 0, 1, 1, 0. So far, are you okay with this one?
Yes.
Let's see what we can fish out of this approach. It's a second order system. We have the boundary conditions. Let's write them down. The u of 0 equals to 0 and u1 equals to 1. So let's say u and v at 0 equals to, u of 0 equals to 0, and v of 0 equals to also 0. Okay. Now uv at 1 equals to, at 1 equals to, u of 1 equals to 1, the other one was minus 1, right? Okay. So try uv equals to column vector eta times e to the I omega that won't work. Okay. It's just not I omega. It's just no I. E to the omega. Was it x there? All right, let's say x. And then uv double prime will be eta. We have omega squared e to the omega x. So we have eta omega squared e to the omega x equals to pi squared over 4, 0, 1, 1, 0 times eta e to the omega x. Bring it together, and we have the following. The eta here is equal to identity matrix times eta, all right? All right, so we'll have pi squared, sorry, 0, pi squared over 4, pi squared over 4, 0. That's one matrix, minus the diagonal matrix of omega squared, 0, 0. times eta equals to 0, 0. Because e to the omega x is never 0. Right? So far, are you catching on what I'm doing?
Yes.
Then this matrix can be written down as minus omega squared pi squared over 4 pi squared over 4 minus omega squared, that's matrix, times eta equals to 0, 0. Now, this is a homogeneous system, homogeneous with the right-hand side of it, and that, or whatever the system is, to have non-trivial solution, we need the determinant of this thing to be 0. Now we get to the same equation. We have omega to the 4th minus pi squared over 16 equals to 0. So omega equals to either plus minus pi over 4 or plus minus I pi over 4. Okay. However, the eta, let's take omega, it's going to be a repeated value. Omega equals to, say, omega squared equals to pi over 4. Sorry, pi squared of pi. This pi over 2, sorry. 4th order of 16 is over 2, right? Let's say the first case. So we'll have then the minus pi over 4, pi squared over 4, pi squared over 4. Just a second. Did I do it right? That's omega 4th, that's pi to the 4th, all right? Okay. So that's correct. This is redundant, and that's going to be eta 1, 1, eta 1, 2 equals to 0, 0. So from here, the eta 1, 1 equals to eta 1, 2. That's the first eigenvector, right? Okay. But we only have one where we have here two values of omega. So I guess this doesn't really help much, right? So I guess this doesn't really avoid what was the problem we ran into here. So we'll have this one, c equals to minus a. We'll have another condition. And we'll have two conditions for 4 variables, right? Okay. And then that's for v. And for a, for u, when we double integrate that, we'll probably won't introduce any new constants. So forget about this. Get back to original approach. So we have the v of 1 equals to 1. And that means you have a cosh of pi over 4 plus b sinh of pi over 4 minus a cos of pi over 4 and plus, see the plus d sine of pi over 4 equals to 1. Okay. That's another equation. Now let's use the fact that u double prime equals to pi over pi square of 4 times v. U double prime equals to pi square over 4 times v, which is a cosh of x cosh of pi over 4 times x, a cosh pi over 4 times x, plus b sinh pi over 4 times x, minus a cos of pi over 4x, plus d sine of pi over 4x. And now we integrate it twice, and we'll have that u will be equal to pi square over 4. When we integrate it twice, when we differentiate, we multiply by pi square over 4, by pi over 4, right? And was it over 2, by the way? All of this 2. I didn't take the fourth order root of 16 correctly. Okay, let's just correct this one. That's pi over 2, 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 pi over 2. Sorry, right? Okay. It's going to be pi over 2. And this is pi over 2, right? Okay. Pi square over 4 times v times, all right, and the double integral of v will be, again, when we differentiate, we multiply by pi over 2 twice. This one we divide. Means 1 over pi square over 4. And that will be second derivative, the integral will be still the cosh of pi over 2x plus b sinh of pi over 2x. And then the integral of cosine will be sine, and the integral of sine will be minus cosine. So it's going to plus a cos of pi over 2x and minus d sine of pi over 2x. That's the u. So u equals to a cosh of pi over 2x plus b sinh of pi over 2x plus a cos of pi over 2x minus d sine of pi over 2x. And now we apply the condition that u of 0 equals to 0. So u of 0 equals to 0, and that's going to be a times 1. The b will fall out, plus a times 1, and that's equal to 0. Therefore, A is 0. All right. And we have as a result that the V equals to B sinh of pi over 2x plus D sine of pi over 2x. And U equals to, as we discussed, B sinh of pi over 2x minus D sine of pi over 2x. All right. And now we apply condition at 1. V of, pardon me, U of 1 equals to 1. U of 1 equals to 1. And that means B sinh of 1 of pi over 2, pardon me, plus D sine of pi over 2, which is 1, equals to 1. And V of 1 equals to minus 1. That means B sinh of pi over 2 minus D times 1 equals to minus 1. So if we subtract these two, we'll get that 2D equals to 0. So D is 0. No, not 0. It's going to be 2. So D is 1. And if you add them, you will get 2B sinh of pi over 2 equals to 0. Therefore, B is 0. So we've done it all. And the result is we have that U equals to sine of pi over 2x, and V equals to minus sine of pi over 2x. Now, those are the extremals of this problem. All right. Have a nice one. I'll see you on Wednesday.
Good day, Professor. Thank you.
Thank you.